All right, today we are jumping headfirst into one of the wildest debates in all of physics. Seriously, it's a puzzle about the very fabric of reality itself, and the two main solutions on the table are, well, they're both pretty mind-bending. One says they're infinite parallel universes. The other, that the empty space all around us is actually a single living thing. So how on earth did we get to a choice like that? Let's follow the evidence. It all starts, like so many things in physics, with a problem that drove Albert Einstein crazy. He famously called a key piece of quantum mechanics spooky action at a distance. Why? Because it seemed to break a fundamental rule of the universe, that nothing can travel faster than light. And that spooky phenomenon? That's the mystery we're unraveling today. To really get what this whole debate is about, we have to go back to the crime scene. This was a thought experiment that Einstein and a couple of his colleagues came up with, known as the EPR paradox. They designed it to prove that quantum mechanics, as it was understood at the time, must have a huge, gaping hole in its story. So here's how it works. On the surface, it sounds simple. You take two particles, you link them together in this special quantum way called entanglement, and then you let them fly apart, to opposite ends of the universe. Now here's the spooky part. The very instant you measure something about particle A, let's say its spin, you instantly know the spin of particle B, no matter how far away it is. And when I say instantly, I mean instantly, faster than light. Now, this led Einstein to come up with what he called a criterion of reality. His logic was pretty straightforward. He said, look, if I can measure particle A right here and know with 100% certainty what particle B is doing light years away without ever touching it, then that property of particle B must have been real and decided from the very start. It had to be. And that was the whole point of their big paper back in 1935. They argued that since quantum mechanics says a particle can't have, say, a definite position and momentum at the same time, but their experiment showed you could know these things about the distant particle, well, the theory had to be incomplete. There must be some hidden variables, like secret instruction manuals, that the particles were carrying with them the whole time. For decades, this was just a philosophical argument. A really brilliant thought experiment, but there was no way to actually test it. That is, until a physicist named John Bell came along, and he figured out a way to find the smoking gun that would either prove Einstein right or prove that reality is way, way stranger than even he could stomach. So what Bell's test really did was put an idea called local realism on trial. And honestly, local realism is just the common sense way we all think the world works. Realism is the idea that your coffee mug is still a coffee mug when you're not looking at it. And locality just means that mug can't instantly affect another mug on Mars. Seems totally reasonable, right? And that was the question, the big one, that sat at the very heart of physics for half a century. Does our universe actually play by these common sense rules, or is something much, much weirder going on just beneath the surface? Bell's theorem finally gave us a way to find out. Okay, so here's how Bell set up this amazing showdown. He came up with a mathematical test. He proved that if the universe is based on local realism, if Einstein's hidden variables were real, then the correlation between these entangled particles could never, ever go above a value of 2. But spooky old quantum mechanics predicted a higher value, somewhere around 2.8. The lines were drawn. All we had to do was run the experiment. And the results are in. Decades of experiments, each one more precise than the last, have all pointed to the same answer. The actual measured correlation? It's right around 2.8, just like quantum mechanics predicted. So local realism, our common sense view of the world, is officially out. The universe is fundamentally spooky, which leaves us with a huge question. What's actually going on? So our first detective on the case is an idea called the Many-Worlds interpretation, and it solves the puzzle by making one of the most staggering claims in the history of science. Let's take a look at its case file. So according to Many-Worlds, the old idea that a quantum possibility just collapses into one single reality, that's wrong. Instead of one outcome being chosen, the entire universe splits, creating a brand new parallel world for every single possible outcome. So when you measure that particle's spin, you're not forcing it to choose. You're just finding out which branch of reality you happen to be on. And in another, equally real universe, your counterpart just found the opposite result. Let's just walk through this, because it's a wild ride. Before you measure anything, a particle is in a superposition. It's kind of a ghostly haze of all possibilities at once. Then you observe it. But that active measurement doesn't destroy the other possibilities. Nope, it just splits the timeline. The universe branches, and each new branch contains one of those outcomes. You just happen to be riding along the branch where you saw the result you did. Mathematically, Many-Worlds is actually really elegant. It's deterministic, it gets rid of any spooky faster-than-light action, and it means we observers aren't anything special. But, and this is a really big but, it comes at a mind-boggling cost. You have to accept that there's a near infinite number of parallel universes completely unobservable to us, constantly branching off from our own every single fraction of a second. But what if there's another way? Our second detective on the scene is a much newer idea called dynamic vacuum field theory. And it proposes something even more radical in a way. It says, forget infinite worlds. There's just one reality, but it's made of something we've been staring at this whole time and never even seen. DVFT basically says that what we call empty space isn't empty at all. It's actually a single physical thing, a dynamic field that fills the entire universe. And in this picture, everything we see, matter, energy, gravity, all the quantum weirdness, it's all just waves and ripples in this one underlying field. Now, the theory describes this field with a single equation that has two really important parts. The first part, called rho, is the amplitude of the field. You can think of it as the actual substance of reality. It's what makes up matter and energy. The second part, theta, is the phase. This is more like the underlying rhythm or the timing of the universe. It's what governs how everything connects and talks to each other. And here is the beautiful solution it offers. That spooky action at a distance? It's not spooky at all. It's just two particles sharing the same rhythm, the same phase coherence in that underlying field. They're not sending secret signals to each other. They're connected because they're both just ripples in the exact same ocean. The link was always there because everything is part of the same thing. Okay, so we have our two main suspects for explaining the spookiness of the quantum world. Let's put them side by side. It's time for the final interrogation, to see how they really stack up. This table really lays it all out pretty clearly. For Many-Worlds, the fundamental reality is an abstract mathematical thing, the wave function. For the dynamic vacuum, it's a single physical field. Many-Worlds is just a way of interpreting the physics we already have, while the dynamic vacuum wants to be a whole new theory of everything. But here's the real kicker. Many-Worlds doesn't make any new predictions you can test. The dynamic vacuum theory claims it does. As for the cost, well, with Many-Worlds you get infinite, unseeable universes. With the dynamic vacuum, you have to bet on a brand new theory that hasn't been proven yet. So the choice is pretty stark when you look at it like that. Do we stick with the physics we know works and just accept the absolutely bonkers idea of infinite branching realities? Or do we take a leap of faith on a new, unified theory that could potentially explain everything in one single connected universe? And that really is the question I want to leave you with. What's the stranger reality? A single interconnected vacuum humming with the potential for everything we see? Or an endless, infinite ocean of branching parallel worlds? When you really stop and think about it, it's hard to say which one is weirder.